All right, so here's our wave behavior thing. So the first thing's asking about what happens when a wave encounters a boundary between two mediums. As that wave comes in, as that incident light comes in, it said one of the possibilities is that it's reflected, so that's the first one. The second one is that it's transmitted or refracts. And that's what refraction looks like. The reflection is what we call an echo. Refraction is the transmission of the thing into a new medium. And the other thing that could happen is that it's absorbed a little bit. Kind of goes into the medium a little bit. So what changes when a wave is transmitted from one medium to another? If we change medium, we change velocity. And if we change velocity, we change the wavelength. But the frequency stays the same. A sound wave in air has a wavelength of 1.25 meters. Find the frequency of the sound wave. In our last worksheet, you had the speed of sound. The velocity of sound is 343 meters per second. So if I want the frequency of the sound wave, I've got V equals F lambda. If I want to solve for frequency, I'm going to divide both sides by lambda. That goes away. So frequency is velocity over the wavelength. So 343 meters per second divided by the wavelength of 1.25 meters. And that ends up giving 274.4 hertz for the frequency. So no matter what happens to this wave, no matter what it goes through, it stays the same. So the sound wave is transmitted into a tank of water. Find the new frequency and the new wavelength. Which one changes? Well, we know that the frequency remains the same. That's what we said here. So the new frequency is the same as the old frequency, 274.4 hertz is our new frequency. The velocity is the same. The velocity is, the velocity changes, so that's 1432 meters per second. So the wavelength is going to change. I know velocity is frequency times wavelength. If I'm solving for wavelength, I'm going to divide both sides by the frequency. That tells me that the wavelength is equal to the velocity, 1432 meters per second, divided by the frequency, 274.4 hertz. And the new wavelength comes out to 5.21 meters. Draw a picture showing the differences in the air and in the water. So we'll do this. We'll call this water. We'll call this air. And so our wave in air may look like that, but when it gets to water, it's going faster. And so I still get the same number of peaks per second, but because the distance between each peak is longer, that's reflecting that it's going faster. Describe the phenomenon of diffraction. Diffraction is a wave bends around a barrier. So if we look at diffraction around a barrier, let's just say we have one single barrier, and I'm just going to draw my wave crest. So this is a lot of waves lined up on each other. For any barrier, for any wave, what we see is a little bit of diffraction. So we see this clipping, and it's almost like it's sticky. And so the wave diffracts around a barrier. And it's that bending that we call diffraction. So I'm going to add another thing to it. The red, that's the wave crest. And so the black arrow, well, I don't want to do black arrows again. The blue arrows show the wave velocity, right? So that's the direction that the wave is traveling. So above the barrier, it's fine. It stops here. So the barrier just kind of absorbs it and it goes away. But as we go this way, what we start to see is a change in the direction. So we have a direction changing. That change in direction because of the barrier is called diffraction. List a common example of diffraction. Draw a picture showing your example. Okay, so during Christmas time these days, you can buy these little lights. During the holidays, you can buy these little lights, and they put a pattern out there, and the pattern kind of swirls around. That pattern is because there's a diffraction grating. So the light's going through there, and it bends around, and that's why you get the little pictures of presents or the little laser dots kind of laid out like this, and then they swirl around. That's diffraction. I'm not a great artist. So there you go. Another place that we see diffraction in water waves a lot is if we have water coming up on a barrier, comes through kind of straight, and then it goes around, and because we get that double curving, it curves away like that. Describe the phenomenon of refraction. Refraction. A wave bends as it changes medium. And so we get refraction only when we have a change in medium. This bend is because the speed changes. This is how your glasses work. This is why when you put a pencil into a glass of water, it looks like it kind of bends at the surface there. List a common example of refraction. Draw a picture. Okay, so that cup of water, which is apparently red. If you put the pencil in, it looks like it's kind of broken in half because the light is sort of bending here. The light is bending there. Describe the phenomenon of polarization. This is a filtering. That's what polarized glasses or polarized lenses do. Light, if you kind of look at it, it goes up and down this way, and then it goes side to side this way. And so when you have a polarizing filter, it cuts away some of the light. So a common thing is to say light moves in these directions, goes up and down and side to side as a wave. If you have a polarizing filter, the polarizing filter has a whole bunch of slits this way. Only this light can make it through. The other light's blocked by the filter. So as the light goes through the polarizing filter, you just now have the up and down part of the light. There's a lot of cool things that go along with polarization. That's why people wear polarized glasses. It gets rid of the glare because it's cutting out that specific direction of light. A man fishing with a rifle shoots the fish in water but keeps missing even though he's a good shot. Explain why. This is refraction. Why the man's shooting at fish, beyond me. But let's say we have the man on the bank here shooting at his fish. Now, the fish is here. It's the best we can do for a fish drawing, right? But light from the fish going to the man bends at the surface of the pond. So here's the light coming from the fish. As it goes into the air, it bends a little bit. And so we have, here, I'll draw it better. So we have this bend from the fish. Now, if the man shoots it where he thinks the fish is, his arrow or his bullet is going to completely miss the fish because of the refraction at the surface. Water waves enter a narrow opening in a levee as a plane, but after passing through the opening, they are circular. Explain what has happened. This is diffraction. Here, the waves bent as they pass through the barrier. What phenomenon causes echoes when you yell into a bottom of a canyon? Echoes are an effect of reflection. That's a wave bouncing off of something.